up next, we have Pak Kau College presenting an efficient and low-cost bio-adsorbent for the removal of heavy metals in wastewater, absorption study of chitin and its derivatives. Thank you.
Good morning, adjudicator. We are from Pak Kau College. This is my partner, and this Sammy, and this Sunny. I am Catherine. Today, we would like to introduce our project, an efficient and low-cost bioabsorbent for the removal of heavy metals in wastewater. One of the biggest problems in recent years is the mistreatment of wastewater, especially those originating from metals industry. The effluent contain toxic heavy metals like zinc, lead, copper, and nickel too, which may cause environmental problem. Absorption is one of the promising techniques because it's simple and with low cost reuse potential.
Our project explores the possibility of recycling the crustacean cells and treating chitin as bioadsorbent to remove the heavy metals present in the effluent. Chitin is also widely present in the cells of crustaceans, like crab, lobster, and shrimp. A working effluent from the annual turnover is in the range of 1 billion to 10 billion tons, making chitin one of the most abundant biopolymers. It has strong affinity of metal ions due to the long paired electron in the OH and NH groups.
We extracted chitin from oysters, crabs, shrimps, cubiculati, and scallops. Its absorption effect was evaluated. Finally, the optimal working conditions like chitin usage, reaction time, concentration, and temperature were determined.
The shells of oysters, crab, shrimps, cubiculati, and scallop are dried and ground, which were then treated with 2M HCl acid to remove its calcium carbonate and washed by distilled water to remove the acidic residues. The samples were deprotonized by 2M sodium hydroxide following by washing it with distilled water to remove the alkaline residues. The standard solutions of 0.02 m, 0.05 m, 0.1 m, and 0.2 m of copper 2, nickel 2, and lead 2 were prepared by dissolving a known amount of copper 2 sulfate, nickel 2 chloride, and lead 2 nitrate into distilled water. Calibration curves of these solutions are plotted by calorimetric analysis and electrical conductivity analysis. Absorption effects of chitin extracted from different crustacean shells were determined. Other factors like mass of chitin usage, reaction time, concentration, and temperature were tested.
This graph shows the absorption effects of chitin extracted from different crustacean cells. The results reveal that the higher metals removal rate was found in carp sample, which is 70%. The absorption of copper 2 is similar to nickel 2 and stronger than nickel 2 at lower mass of chitin usage. However, the absorption becomes saturated at higher chitin usage. As a result, they have similar absorption in foreground chitin usage.
These graphs show the absorption rates of different mass of chitin. We can see that the greater the chitin usage, the better absorption. It may be due to the fact that when surface area increases, more active sites are provided. Therefore, absorption rates increase. The removal rate of 4 grams chitin in 50 ml 0.1 m metal solution reached 75 to 81%. This graph showed the conductivity change of chitin absorption for 24 hours in 30 minutes interval. The solution becomes saturated at 30 minutes and no significant change was found after 30 minutes.
The percent mass of chitin increased with concentration of copper-2. The conductivity analysis showed the absorption effect increased with concentration. The temperature test showed the absorption slightly decreased in higher temperature. We used a temperature sensor to follow the solution temperature with time and found that the temperature increased immediately when chitin was added into the solution. This indicates an isothermic reaction. Similar results were found in calorimetric analysis. The greater chitin usage, the higher removal rate. We can see that when chitin usage increased from 1 gram to 4 grams, the color becomes paler in both copper-2 and nickel-2 solution. All in all, we successfully extracted chitin from crustacean shells. The optimal working conditions are greater chitin usage, 30 minutes reaction time, and higher concentration under the room temperature. Also, the absorption of copper-2 and nickel-2 are stronger than lead-2. Thank you.
Okay, and now we have blanked our samples here. And first, this the chitin that we extracted from this 1, 2, 3, 4, 5 is a chitin that we extracted from different crustacean shells. And this is the chitin that extracted from crab, and it have put it in the metal solutions that is copper-2 and nickel-2 for 1 hour. It's after the absorption. Yes, you can see, and this is the metal solutions, and this is the copper-2 and nickel-2 that before the absorption, and in the upside is the copper-2 and nickel-2 after 1 hour absorption, and you can see that the color have become paler.
Thank you very much for your presentation. So now I would like to invite the judges for a Q&A session. Thank you.
Hello. Hello. My question is that, do you think this is a sustainable solution? Because what we are trying to do is we are trying to extract chitin from living organisms. And if you know the amount of metal that we have as in our waste, the quantity is quite large. So what it means is that if you need to clean a lot of waste water, then do you think this is a sustainable solution for us?
其實係想問下咧，你而家呢一個嘅抽出物啦，其實係個可持續性嘅，因為第一件事咧，你呢一個嘅原料咧係嚟自一啲生物嘅。咁另外一樣嘢咧就係話，我哋呢啲重金屬嘅廢水嘅量都係好多嘅。咁呢一個方法嘅可持續性係點樣樣咧
？Yes. First, this is as I said before, the chitin is the second biggest, most abundant polymers. So there are so many, and because this is also the purpose that we make it. We are living in Hawaii and it's very near to Novo San, and we can see that there are lots of oyster shells there, and it's wasted, so we think about it. And I think it is enough because it's very, there are so many, and we can also take it from different crustacean shells, and also it is reversible. Yeah, we can also we can reuse the chitin. So yes, we can. So yeah.
Oh, there we go. You mentioned it's reusable. Can you explain how you can reuse the chitin after it absorbs the metal? Is that metal going somewhere else, or you're actually reusing the metal ions as well?
You can just, because the ions that we said metals is just in the ocean, right? But when we collect it, we can also reuse it, or we can use it at other way, just like the ions, we can make it to make other things. We can just collect it from the water. Then it's not become the. Just mean if you have collect the metals in the water, then it won't become toxic or waste. Yeah.
Okay, here we go. Thank you for the poster. This is very informative, so it's helpful. I kind of have sort of two questions. First, it's because you wrote at the bottom, greener, lower cost, reusable. So there isn't a cost associated with the production itself or the grinding of the material. So how did you go about calculating that? Because that would be impactful. Although you have an abundance of material, you still have a process. And so I wonder, how do you cost that? And then I'll ask my second piece to the question.
第一個問題問你咧，你個入邊嗰個首先咧，多謝你哋嗰個係呢個咁嘅講解啦。咁咧，同埋你哋俾咗嗰個係呢個係講解字，我哋咁啊非常之有資訊性同埋非常有大幫助。咁入邊咧，我提及留意到咧，你哋提及到係 greener 較綠色，同埋嗰個成本係較低 lower cost。咁咧，我個同埋咧就可以再循環再使用嘅。嗱，咁我有兩個問題。第一個問題咧就係你哋提及到話一個生產啦，就雖然話成本低啊。咁但係問題就係話你點樣去計算嗰個成本呢？因為咧雖然話你哋個成本係低，但係由於個數量好大，咁我哋亦都牽涉到一個製造過程㗎。咁所以呢個成本嘅低嗰度個計算嗰度咧係乜嘢呢？答完之後我再問第二個問題。
Okay, thank you for questions, and just the way that we are using to clean the iron metal in the water in the oceans now is also a very high cost, and it have to use so many things, and all things have to buy, right? And but now the main yeah, the main things we have to use here is just can collect it just like after your dinner, or you can just collect it from the oceans or something, and then it can less so many money, so it must be more less cost.
Okay, can I ask the second to my question? With your summary, you said that optimal conditions would be about 25 degrees, and how does that really compare for natural conditions of wastewater? Is it about that temperature? And why I ask, because again, it goes back to sustainable and whether this will really work over a period of time if the temperature, say, is much warmer of the wastewater.
第二個問題咧就係話你提及到嗰個係嗰個最佳個吸附條件咧係嗰個溫度係20度 20 degrees，right？ 25對唔住係25度㗎。咁呢個問題就係話，如果呢個25度嘅情況咧，如果將來嗰個係嗰個氣温咧係高過呢個係25度嗰陣時咧，咁會唔會係嗰個有個困難？同埋嗰個係你處理嗰個廢水嗰度咧，本身嗰度會唔會係保持喺25度嗰度咧
？25, the temperature of 25 is only the best absorption, but if we, just like we have do the experience that it can also work, it's also work in other temperature, just is the fastest at 25 temperature, but in other temperature it will be lower, but it's also can absorb the iron metals inside the water.
Can I ask one more question?
Yes.
So I assume you conducted your experiments in freshwater samples. Have you ever thought about whether it would work in salt water with a lot of other ions, presumably in the water? Would that affect the efficiency of this absorbent?
你有冇？我哋今次見你嘅實驗咧，其實係喺呢一個淡水，用淡水嚟進行嘅。咁你哋有冇喺呢個實驗嘅過程利用過海水咧？因為海水裏邊可能係除咗你哋特定嘅一啲金屬原料物質之外，可能有其他物質喺嗰度。咁你哋有冇試過用海水咧？唔該。
Yes, I'm sorry about that we doesn't have, because we don't have the equipment to check the iron inside the water. I think if we have to do that, we maybe have to use AAS or something, but we don't have it inside South School, so we just can use the iron, the sodium. So, yes, so we can just use the standard solutions, but we can't use the ocean water to do our experience. Yes, that's so sorry.
I have one question. How did you find the solution? What was the inspiration behind the solution?
你喺今次你揾到一個叫做解決方案啦，可以講。咁你喺呢個解決方案裏邊，你有冇一啲新嘅靈感或者新嘅啟發呢？你今次揾咗個答案出嚟啦，咁喺呢一度你會唔會有啲新嘅啟發呢？
But just for now, we will make a home use filter in the future, just for we use, because we can see that just is also the best temperature is in 25, just room temperature, right? So I think we maybe can make a home filter because it's low cost and just can use at home, and we will do it in the future. Yeah. Thank you so much.
Thank you very much for Pak Kau College. Thank you.